To astronomers, Venus has been perhaps the most frustrating object in the skies. The most powerful telescope on Earth cannot penetrate the dense cloud cover that hides its surface features. In 1973, another mariner, 10th in the series, will set out for Venus, this time to continue on to Mercury, the sun's innermost and smallest satellite. The spacecraft will be the first to use a natural resource of the solar system, the gravity of one of its planets, to help it reach another planet. Venus will change Mariner's speed and flight path, aim it at Mercury, and make it possible to explore two planets for the price of one. The spacecraft will skim past Venus at an altitude of about 3,000 miles, make an abrupt turn, and encounter Mercury on its altered trajectory. A pair of television cameras will take several thousand pictures of each planet. Both will be equipped with powerful telescopes. Other instruments will analyze the solar wind, a perpetual flow of low-energy particles from the sun, producing a kind of interplanetary weather, high-energy charged particles that bombard the planets and vary in intensity as the sun rages and subsides, temperatures of the cloud tops at Venus, and the structure and composition of the planet's upper atmosphere. As the spacecraft approaches Venus, the planet is almost between the sun and Mariner. Only a slender lighted crescent is visible. The crescent grows as the two TV cameras alternately take pictures, beginning about 25 minutes and 10,000 miles from Venus. Cloud motion, cloud layer separation, and sunrise and sunset on the planet will be studied in the pictures. Scientists are hopeful that the Venus pictures may show a glimpse of the surface through a hole in the apparently solid blanket of clouds. Thus far, only radar beams from Earth have been able to penetrate the cloud layer. Bright spots in this radar map, made in 1969, may be mountain ranges or possibly huge depressions. Mercury travels a tight 3-month orbit around the sun. Just a few years ago, it was thought that Mercury's rotational and orbital rates were synchronous. That is, one day equals 1 year with the same side always facing the sun. But recent radar astronomy has shown that the tiny planet rotates 1 1/2 times each orbit. Mariner's high-resolution pictures of Mercury will cover the planet something like this during the first hour after encounter, and like this during the following hour. Experimenters studying Mercury may receive a substantial science bonus. 6 months after Mariner flies by the planet, while Mercury swings twice around the sun, Mariner will have gone 1 full circle and the two again cross paths. This time, scientists will view the planet from a different angle, looking down at the North Pole. These computer-generated plots show how Mercury will appear to the passing Mariner. Early in this decade, the United States will make the first reconnaissance flights to Jupiter in a search for basic facts about the giant gas ball and some clues to the origin of the solar system. 2 spacecraft called Pioneers begin their long voyages in 1972 and 1973. 13 science experiments will study the uncharted regions of space beyond the orbit of Mars during the 600 to 900-day flights. The Pioneers will spend 6 months to a year crossing the asteroid belt, a vast no-man's land of space debris that orbits the sun between Mars and Jupiter. The asteroid belt is 150 million miles wide. Several thousand asteroids are large enough to be assigned numbers, and some even names. An objective of the Pioneer mission is to determine the risk factor involved in traversing the belt. Mission planners believe the chance of being struck by a particle large enough to jeopardize the mission is quite low. Sizes and numbers of particles will be measured by counting penetrations of these cells. 4 telescopes will observe the brightness, speed, and direction of asteroids. Another instrument will measure sunlight reflected from asteroids and cosmic dust. A continuous stream of information will be transmitted back to scientists. Measurements of interplanetary magnetic fields, the solar wind, galactic and solar protons and electrons, and the elements that make up cosmic ray particles. Even at the speed of light, these messages take nearly 3/4 of an hour to reach Earth. Pioneer will pass within 100,000 miles of Jupiter, increasing in velocity as it feels the pull of the planet's enormous gravity. From here, Jupiter fills the sky, colorful in stripes of pink and blue, pale grays, browns, and yellows. Scientists want to know what chemicals produce these colors, why a planet so large can rotate more than twice as fast as Earth, whether it has a solid surface below the seething layers of clouds, and why Jupiter radiates 3 times the energy it receives from the sun. What causes the enormous red spot several times the diameter of Earth? And why does the dark red oval float at random with respect to the planet's motion? Conditions on Jupiter today may be very much like those most scientists think existed on primitive Earth several billion years ago when life began. Pioneer experimenters will attempt to establish proportions of some of the elements that make up this primeval atmosphere. Instruments will measure Jupiter's magnetic field and trapped radiation, both believed to be many times as strong as those on Earth. Temperatures, which may range from -200 degrees at cloud tops to thousands of degrees above zero in the interior, will be measured. A comfortable zone may exist somewhere in the atmosphere. After its swing by Jupiter, one Pioneer will eventually escape the solar system, the first man-made object to do so. And the other may leave the plane in which the planets orbit the sun, passing millions of miles above the orbits of the inner planets. What we learn about the gravitational effects of Jupiter will be used in planning multi-planet missions to the outer planets in the last half of the decade. Observations made with Earth telescopes have provided only tantalizing bits of information about the far-ranging outer planets. We look to spaceflight for some of the answers. Saturn is the only planet with rings. Why? When were they formed? Are the rings the remnants of a former Saturnian moon, or are they made up of tiny ice crystals? The thickness of the rings has been estimated to be anywhere from a few inches to a few miles. On Uranus, seasons of the year must be odd in the extreme. The planet's rotational axis is in the plane of its orbit around the sun, making Uranus appear to lie on its side. Each pole is in sunlight for 42 years, then remains in chill darkness during the other half of its 84-year orbit. Neptune is virtually unknown. It is about the size of Uranus, abides near the frigid edge of the solar system, and is circled by 2 moons. One, Triton, is almost as large as the planet Pluto. It has been suggested that Pluto may be an escaped moon of Neptune. Moons abound in the regimes of the outer planets. Jupiter alone has 12. 4 of them are large enough to have been discovered by Galileo's simple telescope and are called the Galilean satellites. They are Io, Europa, Ganymede, larger than the planet Mercury, and Callisto, larger than Earth's moon. Io is distinctly orange and appears to be brighter when it emerges from Jupiter's shadow than when it goes into eclipse. Saturn has 10 moons. One, Titan, is larger than Earth's moon and is known to have an atmosphere. Overhead, Titan's sky may be like Earth's, blue instead of black. Another Saturnian moon, Iapetus, could be the strangest of all. It varies in brightness as it orbits Saturn. 6 times brighter on one side of the planet than on the other. Why? No one can explain. If a spacecraft were launched from Earth directly to Neptune or Pluto, the journey would take 30 years. But there is an intriguing indirect way of getting to the most remote precincts of the solar system in less than 1/3 that time. Jupiter is the key. Its immense gravity adds momentum to a passing spacecraft, slinging it towards the next planet in a multi-planet tour. The spacecraft virtually steals a bit of energy from Jupiter, which will never be missed. Using this technique, engineers and scientists are planning missions to explore all of the outer planets during the 1970s and 1980s. These missions, each directed toward 3 planets so that all 5 outer planets will be visited, are called Grand Tours. Beginning in 1976 and 1977, Grand Tour spacecraft would fly past Jupiter, Saturn, and on out to Pluto. The complete trip would take about 9 years. Jupiter again is the initial target in 1979. Then on to Uranus and Neptune. By 1988, scientists could be analyzing data gathered at close hand from every major body in the solar system. The dominant feature of the Grand Tour spacecraft is its radio antenna, about 14 feet in diameter. Power is supplied by small nuclear generators that convert heat into electricity. Science instruments are mounted at the opposite end of the spacecraft and on long booms far from the radioactive source. At the Neptune or Pluto phase of a mission, the need for almost total independence from Earth control is essential. The time for radio signals to travel from Neptune to Earth is about 4 hours. Thus, it would take twice that long, 8 hours, for ground controllers to become aware of a spacecraft malfunction and make the necessary correction by radio command. Any trouble in the Grand Tour spacecraft would be detected, diagnosed, and remedied by a special computer, the spacecraft brain. Normal operation would resume without ground control intervention. Besides satisfying the compelling urge of man to explore the unknown, exploration of the planets is returning information to help us better understand our own planet, Earth. How it began, how it is evolving, and how to maintain the delicate environmental balance which provides us such a comfortable home in space. Astronomers and cosmologists have estimated there may be as many as 100,000 other planetary systems, many similar to our own, among the stars of the Milky Way. Future generations will not lack for new worlds to explore. But our generation of the 1970s will have pointed the way.